what we're going to do now is look at Cantor's other main contribution to the study of infinity, which is a theory of cardinality, or infinite size. So this also evolved into the idea of a cardinal number. And we're going to see, well, there are two kinds of transfinite number, the ordinal numbers that we've been discussing, and then there are cardinal numbers. Now, for the finite, these two concepts coincide. The numbers we use for counting, 1, 2, 3, 4, 5, are also the ones we use for ordering, ordinals, first, second, third, fourth, fifth. But we'll see that for transfinite numbers, there will be more ordinal numbers than cardinal numbers. We'll define the cardinal numbers as being proper subclass of the ordinal numbers. But to get back to the basic motivations, we saw in the introductory lecture that there was Galileo's paradox, where Galileo was pairing off, for example, the counting numbers with the squares, or he was pairing off the points on a circle with the points of a circle which was concentric with it, but half the radius. And so the idea was that there was a one-to-one correspondence, and this would mean there are as many as A's as there are B's. And as we saw then, this just seemed to lead to paradox as far as he was concerned. And so the study of the infinite kind of found it, and nothing more was said then. This idea of pairing off was kind of actually using this as a definition for being the same size. Actually, it wasn't due to Gödel. About 30 years earlier, Bolzano, who wanted to make a study of the infinite, he considered the idea of pairing off, saying there are as many as, was a way of talking about size. So, but in his writings, he studied it for a while and then he rejected it. So Cantor was really the first who took the idea seriously, that we'll say that sets have the same size if they can be put into a one-to-one correspondence. So that's the basic core definition of cardinality, and is the main simple but important definition for today. So let's look at the notes at the beginning of chapter 4 and go through and see what some of the consequences of that simple idea are. The section 4.1, Equinumerosity. So the basic definition is there at we say two sets are equinumerous if they can be put into a one-to-one correspondence. Equinumerous if there is a bijection F from A to B. Okay, so bijection is just a one-to-one onto map. So we'll write A is equinumerous with B, right? And sometimes if I want to indicate the function that witnesses this, I put an F over the top. Or sometimes I'll just write F takes A equinumerous to B. So note f to the minus 1, of course, is a bijection from B with A. Right? So it's clearly then it's going to be a reflexive relation. The thought is that we use A to count B, if you like. If this was natural numbers n and this was some other set, I would think of this as a way of enumerating the other set using the natural numbers. So I think of it as using A to count B. And you can see there at the top of the page his discovery that the reals were bijective. So this was Cantor, and there's a date, 1877. Right? So he found this most surprising. And you can see he says, je le vois, mais je ne le crois pas. Why he was writing that in French to his German friend Dedekind, I'm not sure. But anyway, he expostulated in French. For some years, he just assumed that the plane, r squared, would have a different size than r, right? But this turned out not to be the case. Right? I mean, we'll see this later. So he couldn't believe his eyes. Right? The idea that the points of the real line could be put into one-to-one correspondence with the points on the plane. So this was quite remarkable. But we'll come to that later. So this is an equivalence relation. Right? So what are the properties of that? Every set is bijective with itself, just through the identity map. I've just shown above, if A is equinumerous with B, B is equinumerous with A. And 3, if A is equinumerous with B, perhaps via some map F, and B is equinumerous with C via some map G, these are bijections, then I've got that A is equinumerous with C using first F and then G. So we have an equivalence relation. So an equivalence class then is a collection of all the sets which are equinumerous with one another. So an equivalence class under this relation is the collection of all sets equinumerous with one of the sets of the class. Or in other words, with each other. So there's going to be an equivalence class of all the sets which have got size 23. Because to be in that equivalence class just means you have 23 members, doesn't matter what they are. So in fact, each of these equivalence classes is itself a proper class, it can be shown. And what a cardinal number does is it picks out a suitable representative of that equivalence class. So later, if you like what we're aiming for, cardinal numbers pick out suitable representatives of these equivalence classes. Pick out suitable representatives of these equivalence classes. Just in the same way that ordinal numbers picked out representatives of the equivalence classes of well orderings, all of which were isomorphic. Notice that here, being isomorphic as a well order is a more sophisticated concept than being equinumerous. Here you just have to have a bijection to be equinumerous. So in some sense, it's a somewhat cruder theory, if you like, the theory of cardinality. Okay, so this is the fundamental definition, right? This is the basic definition here.
Sorry, please, can you just put the bottom of that last page back?
Sure, sure.
Thank you.
Whoops, okay. Next is we define what finite is. Now we've got the natural numbers. We've used set theory to define the natural numbers, so we'll make use of that first of all. Definition for 3 here. The set to be is finite if it is equinumerous with a natural number. With a natural number. So we know what the natural numbers are. So we'd be saying there is an n in omega and there is some kind of function, and that sends n bijectively with b. If a set is not finite, we call it infinite. So it's called infinite. So infinite means not finite. So I think that's entirely unproblematic and what you'd expect. So now we're going to use basic arguments to derive properties of finite sets and indeed the finite natural numbers. Again, these are things that we would, on a day-to-day basis, would say are just simply obvious in inverted commas. But again, we can prove them, so we shall. So could a set be equinumerous to 2 different natural numbers? Well, it would be very disastrous if that was so. But again, if you think about it, it's something to be proven. We can't have a set equinumerous to 2 natural numbers. And the reason that that argument works logically is this pigeonhole principle. Now, I dare say you came across this perhaps in like first year's Foundations and Proof course, right? But anyway, let's do this again. So no natural number is equinumerous with a proper subset of itself. So equinumerous to a proper subset of itself. I mean, there is something to do there, right? We've defined the natural numbers as being the intersection of all inductive sets. Right? We've seen how we can generate the natural numbers starting from the empty set and using the successor operation. That's the way we could name them, 1, 2, 3, 4, a la von Neumann. But actually, this statement here, actually, we haven't proven so far. I mean, we deploy the methods that we've already have. We deploy induction. So we define a section Z here of the good integers or the good natural numbers, ones that can't be put in a one-to-one correspondence with proper subsets. Right? And then we show that Z is inductive and therefore is all the natural numbers. So one way of saying a natural number n is not equinumerous to a proper subset of itself is to say, for any function f, if f goes from n to n and is one-to-one, then its range is all of n. So the idea being I couldn't map n in a one-to-one way into a proper subset. If it's one-to-one and domain n, its range has to be n. So if I show that Z is inductive, I've proven the principle. So trivially 0 is in Z. So suppose n is in Z and we prove n plus 1 is. So then all n's will be in Z. Okay, so I pick an f. Let's suppose it takes n plus 1 to n plus 1. Right? And we suppose it's one-to-one. And again, it's not a one-liner, right? It's surprisingly, I mean, it's not difficult, but it's surprisingly complicated for a very simple statement. So it divides into two cases. Here is n plus 1. Here's f. And the domain of this f then is the numbers 0, 1, 2, 3, all the way up to and including n. Right? Because this is the set of its predecessors. Case 1 is when I look at f and I see what it does to the things before n, it maps the things before n to the things before n. So I look below n here, and f restricted to n, whatever it doesn't have to be order preserving. So this is f going over here, and this part down here is f restricted to n. It happens to be that f restricted to n is a function from n to n. So what it's saying is that there is nothing down here that gets sent up to n itself. Okay, now I apply the inductive hypothesis to this because I've got a one-to-one function because f is one-to-one. And that says that the range of this must be all of n. So as this is also one-to-one, why? Because f is. by the inductive hypothesis, the range of this is n. Right? N, set of numbers 0 up to n minus 1. So all of these are occupied, coming from something over here below n. So what does that leave f to do with n? All it can do is just send it straight across. It's the only place that f can send n to. Because if it didn't, if it sent n down here, it wouldn't be 1-to-1. But then we've shown that f is onto n plus 1. Its range is n plus 1. F restricted to n covers everything up to n, and f of n gives us n. So that finishes case 1. Case 2 is otherwise. So f restricted to n is not keeping things down below n. For some m less than n. So something got shot up to m here, n here. Let's say this is m that I'm talking about here. So m gets shot up to n in this case, in case 2. And f is 1-to-1, so n, f of n can't be n, it has to go down somewhere. Perhaps some k. F of n equals k for something smaller. Right, so f sends m to n, but n to k. Okay, so we just do a little switch. We just define a function g, which is exactly the same as f, except it just interchanges these two values. And then we appeal to case 1. So define g to be just like f, except that we'll send g of m to k and g of n to n. So g will override f and send m down to k and n across. So now g is in a case 1 type function. Of course, it's 1-to-1 by design. And case 1 applies to g. So the range of g is n plus 1, as we, of course, designed it to be. But the range of g is the same as the range of f, again by definition of g. Right? So this finishes case 2 in the pigeonhole principle. Okay, so 1 or 2 little ideas needed to prove that. Right? Okay, not difficult, but not immediately obvious what is the right thing to say. So there are some
Excuse me?
restatements of this, or some implications of this. Corollary 4.5.
Excuse me? I
Yes?
have a question.
Yes.
I don't really understand why being in Z ensures us that it satisfies the property from the lemma.
Okay. Let me find it again. We're trying to prove that no natural number is equinumerous to a proper subset of itself. So I'm going to look at the collection of n's which satisfy the principle. So I think your question is, why, if this holds, does this mean that n is not equinumerous to a proper subset of itself?
Yeah, exactly.
Yeah. And so this is one way of putting it. This is saying, okay, you give me an f and you tell me it's 1-to-1 from n to n, and I tell you it's not, its range is not a proper subset of itself. Well, to be not a proper subset of itself means that its range is everything. So I'm saying the range of f is n. So this way, this condition is equivalent to saying there's no map from n to a proper subset of itself. Is that okay?
Yes, I think it is. Thank you.
You sure? Okay. I can go through it again if you want.
No, I think it's okay. Thank you very much.
Okay, good. Okay, hope you can still see that end bit. Okay. 4.5. No finite set. Is equinumerous to a proper subset itself. You might think we just proved that. But actually what we proved in the pigeonhole principle was no natural number is equinumerous to a proper subset of itself. Okay, so a finite set is one equinumerous to a natural number. So if I had a finite set here, and this was equinumerous to B here, where B was a proper subset of A, here, by some F here, I know that A is also equinumerous to some natural number by some map G, because it's finite. There exists an N and there exists a G, which takes N bijectively with A. Okay, so organize this little diagram, right, to show that if A was bijective with a proper subset of itself, N is bijective with a proper subset of itself. And that would contradict the last lemma here. So just complete this diagram to show. So if A is bijective with B, which is a proper subset of A, then show N is bijective with some X, where X is a proper subset of N. That's what the exercise asks you to do there. any finite set is equinumerous to a unique natural number. We wouldn't want, if the theory is going to be any good, we wouldn't want a theory of sets where I could have a set and it could be equinumerous with two different natural numbers. Okay, again, this follows from the pigeonhole principle. So, the natural number in the definition of a finite set is uniquely given here. Corollary 4.7 is just a restatement. It's a contrapositive of 4.5. If a set is equinumerous to a proper subset of itself, then it's infinite. Right? That's just what infinite was, not finite. Okay, corollary to this. It's just omega is infinite. Well, there's the function that goes from omega to omega, 1 to 1, and it's the successor function. Okay, it's a 1-to-1 map, but 0 is not in the range of f. So omega is equinumerous to a proper subset of itself, as we knew, and as Galileo knew all along. Right? So far then, we've got the finite natural numbers, and we've got omega, this transfinite ordinal, and the other ordinals beyond that, omega plus 1, omega plus 2, and so on. So Cantor then showed, in fact, one can think of this perhaps as the birth of the theory of cardinality and infinite sets. He showed in 1873 that there were two different kinds of infinity. Right? So this was groundbreaking. Right? So December the 7th, it was a Sunday. Right? So he showed that the natural numbers are not equinumerous with the reals. So omega is not bijective with R here. Although clearly the natural numbers are contained in R, so I can think of them as being a proper subset of R here. But whereas the evens, the odds, the squares, and so on, these are all bijective with omega, this was a new discovery. So a new fact came into the world then with this proof here. And it's a beautifully simple argument, and I'm sure you've seen this before in the first year, if not elsewhere. I'm going to do it again because it's such a nice argument. But it's also the first use of a so-called diagonal argument. And we'll see why it's called a diagonal argument in a moment. But it's, again, a completely new but beautifully simple idea, which he used. So it's a proof by contradiction. So we assume that we can use omega to count R. 1 to 1 onto. So assume this fails, that there is a bijection between omega and R. So I can think of this as a kind of a listing of R, right? Here. I can use the natural numbers to count off R. So on to page 43 there then. So I assume then we've got a listing here. So what we're going to do is we write out the range of F here. And these are whatever they are, doesn't matter. Minus 4 point. And I write them out in decimal expansion. Of the reals. Now the supposition was you'd given me this function f down here and claimed that it was onto R. It was 1 to 1 onto. So it's a listing of every R, every element of R. So supposedly every real occurs in this list somewhere on it. And the diagonal argument shows that that's false, that there is a number not in the list. There's an X in R with X is not in the range of F. So the hypothesis that F was a counting of R was false, and there's no such counting of R here. And the idea is we go down and make X different from every number on the list. So we can let X, we'll let it start out with 0 point something. And we look after the decimal point here and we just change it. We just fix it. So we'll change the first number at the first decimal point, and it's odd, so we'll change it to a 2. So we then go down to the second number, and at the second place after the decimal point, it's an even. So we'll change that to a 1. I go to the third number on the list. I look at the third decimal point here. It's an odd, and I change it to 2. So we continue like this. We change odd digits to a 2 and even digits to a 1 along the diagonal, right in the picture. And I now claim that the number is not on the list. Well, it can't be. If it was on the list, if it was the nth number on the list, it's not, because we made it different from the nth number on the list at the nth decimal place. we made the nth decimal place of x different from that of f of n. Of course, that was our deliberate construction to do that. So that's our contradiction, right? F does not list all of R. So F is not a bijection between omega and the reals after all. So there's no such F. So as I said, a beautifully simple argument right, here, and completely original. And now logicians and set theorists, they use diagonal arguments all over the place. Most notably, of course, Gödel in his incompleteness theorems used diagonal arguments to show that there were statements, for example, in number theory that could be neither proven nor disproven. So that's probably the most famous use of the diagonal argument outside of this set theory here. So Cantor went on from this. It's not just that the reals are not bijective with omega. So there are two different kinds of infinity. We actually see that there are, well, infinitely many different kinds of infinity. No set is equinumerous with its power set. So I take any x. X is not bijective with a power set of x. Now you could say to me, okay, this is fine, you know. If a set has got 10 elements, its power set's got 2 to the 10 elements. So I know there's no bijection. But of course, here we're talking about infinite sets as well. And who knows what happens there? Well, Cantor showed precisely this here. And it's very like the Russell paradox argument.
Should I have a cross?
Thanks. Yeah, correct in the notes. Okay, and similar to the above, suppose for contradiction, F was a bijection between X and its power set. So somehow I use X to count its power set. So now we let Z be the collection of elements of X where U is not a member of F of U. So recall in the Russell paradox, we looked at the collection R of elements in the universe, U, where U is not a member of itself. There's a sort of variation on that argument there. Although indeed it predates Russell's paradox. Now, what have we done? We've got this Z here. It's a subset of X. So it's in the power set of X. We're supposing that F is onto. So Z is then F of something. So as F is supposed onto. So this is a U. And now you ask the question, is U a member of f of u here. So question then, is u a member of f of u, right, which is z? But of course, to be in z means u is not a member of f of u. Is not a member of f of u. Okay. But if u is not a member of z, that's because u is a member of f of u. So this is a contradiction either way. We deduce from the fact that u is a member of f of u that it's not, and if it's not a member of f of u, then it is, right? So this is absurd. This is a contradiction. So there's no such f. Right? There's no such barber here. So what we've got then is a whole series of infinities at the very least, right? I've got the natural numbers here, and I've got the power set of the natural numbers. And what we've just shown is there is no bijection from these two. But of course, given any, I can think of omega as being more or less, every element of omega is a singleton that's over here. So somehow this set contains this one. So this is going to be a kind of bigger infinity than this one. But now I apply this theorem again. This is not bijective with the power set of omega. This is a yet bigger set than this. And of course it goes on. Forever. So the power set operation is bringing us larger and larger sets of larger infinite size. So it wasn't just that there were two kinds of infinity, there's infinitely many kinds of infinity. And what the rest of this chapter will be doing is trying to bring some order to this picture. And we'll work out exactly how these kinds of infinities fit together. Fine. So next time we will continue and we will look at the Cantor-Schroeder-Bernstein theorem.